Okay, thank you. Okay, thank you, Zhiqiang, for your introduction, nice introduction. Also, I'm happy to see e-meeting, face meeting with all my old friends and so on. Director Andreas Savakis is my old friend when I was at Rochester. We know each other that long time ago. Okay, well, today's my talk is go something like this. Okay. So I'll talk about a new paradigm, especially how this visual computing evolving from algorithm to systems. And then I will talk about the historical evolution of how we got to this stage today, including the different part of visual computing, from sensing to analytics to networking to storage and to rendering. Okay. Then I will focus on a different area of this the contemporary visual computing, including the embedded visual analytics, including the joint source channel coding, and also the terminal edge cloud architecture and mobile rendering. Eventually, I'll talk a little bit about Internet of Video Things. And then I'll give a summary and take-home messages at the end. And then I'll be happy to answer questions at the end. Okay. Okay, let me go over a little bit about this, how we are evolving from algorithm to systems here. Okay, that actually is how we see how important is visual signal processing. And this is also how I was drawn to this field many, many years ago. So essentially, 90% of the information we send to our brain is actually visual. Okay, you are probably not realizing that. And also between our communications, I think 93% of those actually in visual is also visual. Okay. And then I'm pretty sure you have a different experience when you only hear noise, hear voice, or when you also see a different person in front of you. That's actually how video communication is much more powerful than the others. Okay. So this is one of the things that we have embedded in the brain, how the visual importance is. Then if we look at the many emerging applications from environmental monitoring to smart home, wearable device, smart grid, medical and healthcare, connected vehicle, smart city, and industrial application, each of them currently will have different type of visual acquisition process to make it the whole system much more intelligent and also reliable. Okay, so the importance of visual computing in the current application is also being very clearly demonstrated. Okay, so let me go back to very conventional visual computing definition here. Is essentially is a generic term, okay, for any computer science discipline dealing with images, videos, other type of visual data, graphics, and so on. Okay, so in initially, all those visual computings actually refer to algorithm development. So essentially, you have visual data in, we design certain algorithm, and then either we have visual data out or non-visual data out. Okay, so that's how we have been doing this for many years. It's just algorithm development. Well, the world is changing. The world is changing in a sense that we now have to look at the entire ecosystem from the generation of the visual data or sensing, and then to the analytics, to networking, to the hosting of this visual data. So of course, we don't just go one way. We actually have the return to this from visual data host, and then we enjoy by many people, those visual data actually had to go through the back forth from networking to maybe analytics and to eventually rendering, because when we present this visual data, we might have to do all kind of processing, rendering, analytics, and so on. Okay, so with this software to embedded and then next, from software to embedded processing, networking from wired in the historical and then into wireless everywhere right now. The storage from very local storage to now cloud-based or multi-cloud based or whatever. Okay. Then visualization will to a simple animation now to AR, VR, and the metaverse or digital twin. Okay. So the new paradigm in this video computing also give us a hint that we now have not just this feedback, we now have this cross-layer issues to deal with. Okay, for example, the examples I'm going to talk today essentially will be have to touch on different block uh, of this ecosystem here. Okay, for example, embedded processing, you might have to consider all kind of things here. And then the system consideration, instead of just any individual performance measure will be the main, the driving force for all this. For example, in the sensing end, we have sensing quality. We might have to consider latency, energy efficiency, processing capability, caching capability, and so on and so forth. In terms of the processing and elected, we have joined embedded processing, visual data compression, event detection, and so on and so forth. Okay. Then of course, if we wanted to push the intelligence to the end to the front end, then we have to have lightweight deep learning, joint source channel coding for networking, terminal edge cloud for resource allocation, and eventually for presentation part of that, many of them is actually doing mobile AR, VR. Then we have immersive visual presentation, metaverse system design, and so on and so forth. The issues become a system performance instead of just a single measure. Okay. Okay. So let me, before I going into
Dr. Chen, Dr. Chen,
yes.
I apologize. It's Sue, but I can't see your slides. And I know we had them before.
Oh,
So before you started talking, so it's not being projected.
it's not being projected.
Right.
So it's interesting. Anybody else or just you? I see here is you are sharing. So let me
I
stop.
can see the slides.
Oh, you
I can
can.
see the,
Okay.
yeah,
Okay.
I can see the
Excellent.
slides.
Okay. Then I will.
Everybody else see the slides? We may get response from the audience.
Okay. Very good. Thank you.
Let's see from the Q&A. Yeah,
Everyone else can see the slides. Okay. Must be
yeah, I
my.
think it's good.
Okay.
Hmm.
Very good.
Okay, so Zhiqiang, you can see, right?
Yeah, we can see. I think we're good. Yeah,
Okay, so are you with me right now on this history slides, long history? The slides long history right now.
yeah,
Okay, so we have this the long history of that. Of course, the camera is the visual sensing device, started in analog form and then evolved into digital camera. Of course, many of you probably you don't know digital camera invented in Rochester. Okay. And of course, the evolution of camera essentially parallels that type of computing system and networking advances here. And also recent advances in virtual computing are driven by both hardware and software development, not just software. So from embedded processing to joint encoding and understanding to cross-layer. And also I bet that future advances in visual computing will certainly be propelled by the application of AI and learning technologies. Especially for visual data, we need to learn very rich semantics from those visual data and apply them, apply those AI technologies to get to the new next stage. Okay, so I'm talking about evolution of sensing system here. Let me begin with the analog, which is invented 100 years ago. The cameras also invented in this time. Okay, Kodak is the way. And then, of course, in digital time, we have the CCD and CMOS and so on. Many of them take new technology also even in this time. So I'm very proud of Rochester and my Rochester connection here. Okay. Then, of course, more recently, we are involved into surveillance cameras. Then we have massive of those cameras. Okay. Uh, then more recent years, we also make a camera to fly, which is that means we have these drones. We can with the camera can look at every directions what we have. Okay, and then of course, let me show you a few interesting things here. This is on left is the principle of the camera, and then on the right, this is many years ago was over 150 years ago. We have this old camera. Okay, we have digital camera, which, as I mentioned earlier, is invented in this time. And then, of course, we have all kind of professional digital cameras right now. Okay, and then more importantly, we now have everywhere we have camera and also in the sky. So we have this sensing system actually being evolving from the single ones to massive ones and then from stationary to flying ones. Okay, so we get the very rich history on this sensing system here. On the analytics, okay, of course, in aerial analog cameras, the photographs need to be first digitized, okay, and that's the one we have actually doing right now. Of course, right now is embedded in the very front of this camera. In the case of digital camera here, of course, the output itself is already digital. There's no digitalization is necessary. But we creating massive data, so we need to compress them. So we have a JPEG and MPEG, and this is also being very advanced right now. Okay, so an analytics operation have been pushed to the front end of visual data. Now that's why we need embedded processing. Okay, because many of this the data acquisition will needed to capture some event which can happen anytime. Okay, so that the embedded analytics from the front end performing integrated visual data, especially for event-driven monitoring cases here. Okay, so with this, I think I'll be happy to share with this first scan done by SEAC in 1957, before I was born actually. And then on the right here, we have this SEAC scanners, how it works. Of course, it was rudimentary at that time and also bulky. Okay. Then with the coding part, I'd be happy to share that we are much more advanced right now. What I show here is very basic principle of JPEG and MPEG. Of course, now we have grown to say the H.266 and more. For the embedded analytics here on the front end has also recently been developed to form low latency tasks. And of course, latency is required for the specific task. Some of them is much more demanding than the others. Okay, so those are doing an analysis or also to consider this the latencies in this case here. Okay. Well, then let me move on to the networking part of the story here. For the analog visual data communication time here, we actually are doing analog modulations. And in that case here, visual signal often transmitted over air. That's where the TVs and so on was invented, and satellite images also was done that time. Okay. For digital visual data networking, IP networks will enable the transport of digital video shared by various terminal devices here. So digital video can be transported either over the air or via the IP networks here. Smartphones now is frequently used to upload personal video, and that means individuals now become broadcaster right now, and that make it the networking change actually over very interestingly used to be the star like. Okay, you have everybody's downloading, now it's everybody's uploading. Okay, for this networking case here, many cases that we have to consider joint source channel coding because compressed visual data and the visual data need to be compressed. Okay, it's much more sensitive to the channel errors, and in that case here, if we don't do joint source coding with a limited resource here, we don't have the capability to optimize the transmission of those data here. And of course, the joint source channel coding achieved by rate distortion optimizes resource allocation. Okay. So this is actually analog ones. Okay, doing analog communication or networking here, you have analog input to be input transducer to convert that into the form that can be modulated, and then you are going through the channel, and then demodulate it, and then go back to the output transducer here. This is the analog. For digital here, of course, digital networking here, we had to compress, and then we had to convert it into the digital processing, and Then we have digital communication and back-end digital processing, then receiver, then display. Okay, so it's a similar process, except that the one with digital is always digital form. It's very easy to do, especially with the current IP networks. Okay. Then, of course, let me show you what is a separate source channel coding and a joint source channel coding. In fact, for people working in the information theory or communication or signal processing, they probably all know that according to Sharon, okay, the founding father of the the information theory here, tell you that you know, you can actually separate, optimize the source and the channel coding and still get the same thing. But assuming that based on two assumptions here, one assumption here you can wait infinity long time. The other is the complexity can be on either end. It can be complicated. Okay, of course, in practice we don't have this. That's why for many people, why we're doing joint source channel coding, because in practice we don't have the luxury of the wait, the delay for them to optimize and on single, you know, either source and then first source and then channel. Or we don't have the complexity we can afford to go through this room. So joint source coding is just wanted to make sure that with limited resource, we can do our best work in terms of the meeting also latency constraints in all different applications here. Contemporary the video surveillance here, you could handle multi-sources here, okay, in this case, okay. So no problem with that with IP networking, okay. Of course, the most contemporary ones is cloud-based video data networking application. And in fact, for surveillance, they do have a name for this. It's a video surveillance as a service. Okay, you know, for the cloud computing, everything is a service, and video surveillance can be designed as a service within the cloud computing paradigm. Okay. Okay, and then of course the host, you know, this is actually in the tongue is well known. So the analog camera use film. Okay, so this analog form of visual information recording is on the film photography and subject to various degradation over time. So they used to have, I'm pretty sure Russia used to have many of the chemical engineer here, and then later on when the digital came, they more this electrical engineer came to this time. Okay. So for digital camera, of course, to capture photos in digital memory device manufactured by a different type of semiconductor. So this memory device have the property of random access, allowing fast retrieval and transfer of data over a computer. More contemporary visual data, of course, will be hosted by the cloud. And in that case here, in addition to computing storage, they also need to meet high performance networking and security, because those are typically some distance away from your application. Okay, so looks familiar for many of us, okay, especially these people in Rochester, okay, photographic films, and then of course movies. This is actually storage ones we have for digital ones. And we don't see a DVD often right now, maybe zero, okay? But we do have this USB drive all over the place. And then certainly we still have portable hard drive, okay? And of course, for the cloud-based, of course, for example, a company like Netflix, they need to have a lot of this cloud service, cloud-based to host their contents and to deliver. And of course, similar ones in China is Tencent. Okay. Well, then we come to rendering. Okay, rendering, of course, in the case of the analog video tape recorders, and I think I'm pretty sure I still have him in my basement somewhere with this, but we don't use it anymore. Okay. The digital visual data representation, of course, enables not only high fidelity playback, also a broad range of rendering manipulations here. Okay. Finally, we have contemporary digital video rendering is penetrating into smartphones, emerging AR, VR, digital twin, metaverse, and so on and so forth. So those are the trends, and then let me share some of this. Of course, TV is one of the main forms of the rendering for a larger part of the last century. And actually, I work with startup before. I know it's much more history of that. Of course, analog video tape recorder, old people still remember, but they are probably no longer used right now. And in order to receive the visual data, we had analog TV antennas. Okay. Of course, later on, you have this coexisting part of years, I think from 2000 to 2010, there was coexisting analog and digital TV. Now it's all digital TV. And then, of course, more importantly, is IPTV, which it doesn't have to be TV terminal to watch all this. Okay. Then, of course, we have this, the internet video, which have smartphone, video conferencing. This is the Zoom we are using right now is many of this, the more recent development of the visual computing. Okay. Then of course, more advanced the 360 video, we have more one rendering and industry 4.1, and so on and so forth. So rendering also going through a dramatic change here. Okay, so let me summarize the visual computing evolution here. The overall visual computing actually from sensing to processing to networking to hosting at the cloud centers. The evolution of visual computing mirrors whatever we have done with the computer. Okay, so that's how we see it. The contemporary application of visual computing depends on visual data centers hosted by cloud and or any related networking mechanism. So it's no longer just algorithm, it's really a system here. So advanced in many different fields, including computing, communication, storage, and deep learning AI will need a more advanced in the future visual computing here. More importantly, we don't just taking care of the component of those systems here. We had to looking cross-layer designs, okay, in order to achieve the overall performance here. And deep learning AI will play much more important. I will have some example in the next. Okay, so with this, I'll tell you a few things. Some of them I'm currently working on. Some of them is we are tracking on. Okay, so the technical challenge here, they are different part of here. Okay, first of all is the joint source visual data coding embedded analysis. So you are pushing the visual analytics to the front, and in order to get the just-in-time event detection and the intervention, possibly if needed, and for any task-specific application here. For the second part, I'll talk about is joint source channel coding for very unconventional semantic communication, and this semantic communication is based on the visual data. And the semantic communication will have much more effective encoding than the conventional ones, okay? So in this case, you are transporting the semantics behind all this massive visual data to a remote monitoring center for effective and reliable visual computing, okay? So the second area I'm going to discuss in next. And then the third area I'm going to discuss is the terminal edge cloud architecture, which is across the entire spectrum of this ecosystem here especially for low latency reliable networking here. Okay, because you have to distribute the resource to each part of that in order to have most advanced, most effective work. Okay. The next part I'm going to talk about is the mobile rendering in the mobile device here. And then certainly in this case here, we'll have to integrate immersive data acquisitions with mobile rendering through learning-based approaches here. We're going to talk a little bit about that. And finally, I'll talk about internet video things at the end to illustrate that the system aspect of this visual computing. Okay. So the first part, the joint encoding and embedded. This is a diagram for this embedded analytics on the front here. Of course, you can see that we have 7 conceptual modules here sitting in the embedded device here. Okay, so we have cameras, embedded codec, processing and analytic communication, power, storage, and interface. Okay, so performance issue here will include operating time, Okay, energy consumption, data storage, visual field coverage, visual data fidelity, and so on. Okay. And with this, we actually this is actually coming from the I have the reference here. Okay, so with this, we have one example here doing quite good in terms of coding and embedded in the net here, and this is called City Brain. Okay, this is an example of contemporary visual computing system here. So they have very efficient video data encoding and a compact feature extraction. So in the middle here, let me see, I can probably. Okay, so in the middle here, you see the three channels here. One is a feature stream. The other one is a model stream. And then finally, we have video stream. So feature stream naturally is the result coming from analytics. The model stream is for the AI-based here. We have this model, so we can also send it to the center. And then finally, we have video stream here is a compressed video data. Okay, so with this here, you can do both, and also the embedded visual analysis implement at the front end is required. Okay, model adaptation and update also. So three stream here to be sent to the center for monitoring. Okay, so this was published a couple of years ago. Okay, so with this, I think I like to share with you several with just two examples. Okay, technical challenge in this case here. First one is the design of visual data encoding scheme here. In this case here, we are being historically doing coding for human observers. Now is coding for machine intelligence, because many of this say event monitoring case we don't. It's not for us to enjoy. It's actually for machine to take actions. Okay. The second part of that is the task-driven selection of the analytical algorithm here. Just-in-time event detection will certainly be very, very good for this event monitoring. But if we for more general case here, maybe features extraction is necessary or is desired if we don't know what to expect. Okay. Then, of course, we can address this algorithm complexity issues here because this is in the front end. Okay. Deep learning model has to be lightweight, and of course, we also need to consider the energy consumption issues here, low power design or performance-driven implementations. We can also adapt the needs of visual data networking because those are being connected to the center somewhere. Okay, so of course, you may have wired stable or you may have wireless, but it's going to be mobile or easy to move, but it's error prone. Okay. The second area I'm going to talk about the joint source channel semantic communication here. Look at here. This is actually different from conventional communication in the sense that they have dual channel here. One is actually physical channel. The other one is actually semantic channel. This is specifically designed for visual data. Otherwise, we don't have semantic channel here. The semantic channel being made a virtual channel because we are sharing this background knowledge in the visual data instead of have to send over. Okay, so in this case here, we recently worked on this deep learning enabled semantic communication process here. The key feature here is coding and transmission of semantics instead of digital data. The representational semantics is in those first few initial trial attempt here is based on natural language processing techniques here. Okay, and of course we have dual transmission channel, as I mentioned earlier, is a physical channel plus semantic channel, virtual channel, and the semantic knowledge will have to be shared. But semantic knowledge can vary from one application to another. Okay, so this is actually in this example here. The second example here is essentially more specific ones. In this case here is for the key feature in this case here is using this the AI to do bandwidth adaptation through deep learning technology here. And this AI-driven channel stats learning and adaptation will be able to enhance the overall performance here. And this is done just published just a couple of years ago. Okay, so with this two simple example here or brief example here, I can see the technical challenge here in this area here. Of course, first of all, the needs for semantic communication is already being outlined in the 6G. So we expect that in a few years, okay, 6G for massive data dominated by visual content, I think has been talked about 70%. I last checked in the 2023's report by Cisco. It's 82% right now. Okay, so we got to deal with it if we're 80%. And one of the things that this is actually beyond traditional semantic communication here, because traditional semantic communication is probably the language semantics. Now for visual communication is non-lingual pictorial semantics, which is much more difficult to extract from visual data. Okay, because in the case of the computer vision people, we are talking about semantic gap, and we still wanted to close this gap. And there are many ways to do this representation of semantics. Some of them is by features, some of them by maybe have a human object interaction. Some of them is by we call scene graph generation, which I just give this ICME in keynote is about scene graph generation for semantic communication. Okay, and many of them actually based on the deep learning technology here. Okay, and then of course we have to redefine channel coding because now the representation is different. We have to design new ways to map the semantics to the practical digital coding constellations, okay? Because if we want to make use of the current communication system, networking system, we had to do this part, okay? Then, of course, we have deep learning-based channel adaptation. I just give example previously. In that case here, in order to minimize the error and maximize the bandwidth, okay? So this dynamic wireless networking is we have to deal with, okay? Okay, the third area is about terminal edge cloud networking. If you see my ecosystem here, this is actually crossing the entire ecosystem chain here. Okay, so in this case here, essentially, one perfect example is IoT application. You have IoT device as a terminal here, and you have cloud processing for these IoT applications. In between, you will have to probably deploy some edges in order to make it the networking part of here working. Edges typically is close to the terminals here. So in this case here, we have just illustrate here the edge node with broad functions. We have make computing, caching, networking, managing, so on and so forth. And essentially is balancing the functionality with resource allocation, computing versus networking, or maybe also versus the caching part. Okay, can we temporarily store it somewhere? So in this case, of course, you can see that systematic design over the whole networking vertical continuum. Yeah. And the second example in this case here is good for what? It's good for the web AR applications based on distributed DNNs is of course deep learning neural networks and the 5G. Here we actually join in the design the optimization of hierarchical performance for overall performance. Okay, and this is actually being testified that is working well. Okay, so with two brief example here, I can show you what is challenger here. The challenger here, of course, is first thing is systematic source reallocation. Okay, and source including this moving those time sensitive or massive visual data too. So latency has to be important. Okay, also in the needs and designing deep learning based smart networking scheme here. Okay, so intelligent networking comes at cost expensive, some computing, okay, at the terminal or at the edge. Okay, also has a possibility of adapting intelligent refracting surface IRS as a passive node here because in order to save energy at the same time doing better work in terms of that the IRS is usually very useful This is actually a passive edge node for urban, especially for urban environment when you are many tall buildings, and then the terminal is on the ground. They have to penetrate in many ways to the top of the tower. Okay. So also we balance node functionalities between computing, communication, and caching. As you are in the communication area, you talk about, you know what I'm talking about, 3C here. So 3C means making use of the resource from computing, communication, and caching to achieve overall system optimization here. For any task-specific optimization here, this will make it easier because for task-specific here, we know what is emphasized or what is focus of the performance here. Of course, we have to have this visual data maybe across the entire networking spectrum here. And distributed video computing with optimal partition coding and analytics will be very necessary in this case here. So in most cases here, it is actually signal processing over networks, which is how to be implemented here. Okay. So the fourth application is learning-based mobile rendering here. And in this case here, remember the keywords here is mobile and the rendering. Okay, so the typical mobile rendering with interactive feedback means if you do rendering with feedback, it's very, very important that people are using this actually can be, at a very good spirit. Unfortunately, now we know that we still have this virtual environment sickness problem we haven't been able to solve. Usually, most people can only, under this situation, only maybe 15, 20 minutes. Then you feel that the reason for that is because the display is trying to perceive in 3D, but our brain always think this is only 2D. So you have debating this and the perception and the reality discourse here. Okay. So the key challenge here, of course, is the user feedback had to be, instantly feedback to the data center. Okay. So in this case here, it's difficult that if you don't have the nice feedback of user intention, then the delay or latency will be too large for people to see this. Okay. And of course, with the 6G is coming, and then we have this the digital twin type of thing or metaverse here. So in this case, we have distributed digital twin here, mobile edge servers, and also Meta QoE, quality experience here. The key challenge here is rendering on lightweight and a wearable mobile device, which is much more difficult to do when it's on the mobile device. Okay. Well, with challenges here in this particular area are the following. Okay, you got to have a power computing constrained mobile rendering system here. In that case here, everything should be lightweight and wearable. But it's very difficult. If a wearable means that you have to have a mobile networking here. And also, it's very difficult to understand human intention, especially with the device. And then it will turn left, and it will show you the picture or visual data in the left. So to right, then it will show you that. But the intention of us, we might not be following all this desired pattern. So that's a capture the feedback, and then instantly feeding the data is non easy work. Okay, we could have a multi-model interaction here, visual, lingual, haptic, and so on. So in that case here, interactive design beyond passive sensing of hand motion. This is what we do right now, is we do hand motion and eye tracking, but it's much more than that. Okay. Also, we need to push powerful computing storage closer to mobile device, and mobile edge computing for low latency and energy efficiency is needed in this particular area. Of course, everything had to be based on human-centered design. Okay, I think I'm very happy to see IIT has this human-aware AI, because many of AI are not smart enough to understand human. Okay, so human-centric design guided by visual perception principles have to be there for this type of application. Well, the last area I'm going to talk about, and I hope I'm not too much over time. Okay. So last area I'm going to talk about is going to be the Internet of Video Things, and it's actually Internet of Video Things is consisted of this three major portions of that. One is sensing, the other one networking, and the integration. Okay, this is that from algorithm to network system with the computation and the caching design here. And this actually is the one of the things I proposed a few years ago. Okay, and I wrote a first single author paper for many years. I have none. Okay, so until 2020, I have my first single author paper. This is actually being asked by the Internet of Things Journal editor-in-chief. Okay, they say, okay, Professor Cheng, I know you have this. You have to write a paper for me. I say, I talk about it. I have PowerPoint, but from PowerPoint to paper is not non-trivial. Okay, everybody knows that, right? But I did. And then a few months later, after publication, and another journal is called IoT Discovery IoT. I said, Chang Wen, it's not fair. I'm also EIC for this. And then you wrote him a paper, you had to write me a paper. So I said, I cannot republish. So I write something specific things here. So in this case here, I say, what if the IoT is actually the front end is a drone. So I wrote this smaller paper. Okay, so in this case here, as active IoT node, capturing visual data continuously while flying over targets, dynamic operation mode with for data acquisition, information transmission, and the knowledge extraction. Everything is dynamic in this case. It's a flying. Okay, so drone as an Internet Video Things front end. So this is also the second paper. I'm not going to publish my third paper. I don't have plan, but who knows? Maybe another editor-in-chief will ask me to do something in the later. Okay, okay. So, but this IoT things has been going on for many years. I think since 2018. And some of the recent work my student and I have carried out is essentially is putting into real system. Okay, so in this case here, we actually doing this NORMA assisted. NORMA stands for non-orthogonal multiple access, so for networking case here. So in this case here is because of the IOVT, if we apply to the user here is actually we have to user-centric here. So user-centric network is different from the conventional network, which is actually top-down. Okay. So in this case, it's offloading visual processing to the mobile edge server here, overcoming the limitation in the uplink capacity of the current system with NORMA assisted framework. Okay. And this is done 3 years ago. Okay. So with this example here, I can summarize the technical challenge here, dealing with the continuous generation IOVT. Many cases of this IOVT, different from IoT, is that the data generation is continuous. They don't stop, okay? So they were demanding very robust networking and real-time computation. The networking of massive number of IOVT is not just a few cameras. There actually may be dozens or maybe hundreds of cameras within a system here. So of course we have 5G here. Okay, 5G actually one of the 5G standard is or scenarios is for massive machine type communication designed for this type of the. So I think we have the infrastructure to do this IOVT. Okay, we also need to resolve this issue related to fragmented information island. I think this particular happening in China. Okay, when they're different, the government agencies and they put a different, they put their own cameras, and there are too many cameras on any of these intersections here. Okay, they are fragmented and they don't share. Okay. Then, of course, visual data, one feature of visual data is that you can immediately recognize things over there. Okay, so privacy and security is concerned. So that's why in Hong Kong, which is just next to Shenzhen, it's very differently is that the street or intersections have many of them has 0 cameras, and the only major ones maybe have 1 or 2 cameras just for the monitoring. Okay. So security and privacy concern is also, this is also for retrieval purpose here. because you know, this is actually it's very important that you know, we can see that thing, and then we don't need any coding or encoding. We see what's going on over there. Then, of course, in order to make it everybody can use some technology here, standardization is very much needed. Okay. Okay. So with that, I think I will end my talk in a minute. Okay. So let me just summarize what my talk today. Okay. In fact, this is actually the three messages here I'd like you to take home. Okay, so first message here, the contemporary visual computing has gone drastic evolution here from algorithm to system right now. It's no longer just a single performance measure. We have the system-wide performance measure here right now. Okay. The also more comprehensive performance issues from systematic perspective here. Of course, real-time sensing, no latency processing, energy efficiency networking, 3C in terminal, edge cloud networking continuum, search retrieval, security and privacy, mobile rendering, and visualization. Any of this will be very interesting topic to conduct research. Okay. Of course, we get many applications. I show you briefly with 5 here. Okay. But any of them will be very much, you know, following this AI and the deep learning. Okay. With this, I think I'd like to thank you and be happy to entertain questions.
Okay.
Thank you very much.